Vancouver. My apology, I'm actually seeing quite delay in terms of the speed. Is it from the internet, from your side, or too many people on Zoom? Whatever I'm sharing, it is not immediately shared with you. Not sure why. Are you still seeing the picture of Toronto?
Yeah, I could see the city and also the bridge.
Yeah, so it's very strange. Oh, you can see the city with the bridge. Okay, so this is Vancouver then, finally. So you can see with so much population growth worldwide, we're expecting to see a lot of new infrastructure need to be built. It is expected about 2.1 trillion square feet of new construction need to be built by 2050. So for many of us, we don't really use the unit of trillion square feet. Just so you know, Jakarta is about 800 square meter, okay, a kilometer, 800 square kilometer. Singapore about 700 kilometer square. So 2.1 trillion square feet means is that we need to rebuild or build 9 Singapore every year around the world for the next 30 years. So there are a lot of construction need to be built. And these constructions are creating global warming worldwide. I'm going to pause a little bit because it seems like the presentation slide showing up in your conference is slow by a few seconds. I don't know why. I think you're still seeing a picture with City of Vancouver, right?
It's already changed to, yeah.
You can see it now. So now you can see the whole world are seeing a huge carbon emission growth. So you can see United States, China, actually Indonesia in high production of carbon emissions. These carbon emissions are causing global warming and it's causing an issue. We see forest fire, we see a rise in seawater levels. So many countries have decided to work together in achieving green carbon gas emission net zero by 2050. Okay? In order for us to achieve net zero by 2050, what we need to do is by year 2030, we needed to start cutting the carbon emission by 30%. If we don't do that, part of will be undue. In addition to the new build, in addition to the carbon impact caused by the war, we are seeing our existing infrastructure in North America are deteriorating very fast. Right now, based on our initial search, it costs about 141 billion Canadian dollars to actually replace existing infrastructures which are rated very poor. We cannot reuse them again. And we need another injection of $11 trillion new population growth. In addition to this population growth and maintaining of the infrastructure, we're also seeing our infrastructure experiencing lots of loss, financial losses through natural disaster, earthquake, windstorm, fire, flood. We see all the time. Within the period between 1998 to 2017, less than 20 years, globally, loss for infrastructure reach about close to $3 trillion US. So the next generation infrastructure that we're focusing on developing, we started using new way of construction. So we pre-made those in a factory and quickly assemble on site. We're developing 3D printing technology to allow us, we're reusing material, use of a massive timber material to reduce the carbon intent to the new infrastructure. Of course, at the same time, we want to make sure those infrastructures have all the technology we can to make sure they are safe for the next round of earthquake. So we start developing energy dissipation devices. Finally, we're using monitor in real time, so the next generation infrastructures are smarter, they are carbon neutral, and they are resilient. Back to the pictures we see, the conventional constructions, this is the picture in United States, but no different in many other places. We lack of skilled workers. In North America, we have very few skilled workers are working anymore. We also, conventional construction needed a lot of time for construction, and you have a lot of waste in the construction material, and a lot of time, very poor quality assurance, and many times it's affected by the weather and lack of construction site for us to build. So over the last 20 plus years, the world start developing newer way of building faster to meet the global demand. This is a video showing you the technology design and assemble the structures together. This is a real line time showing how fast construction can be built. This is a 15-story building within 2 days, less than 2 days, 46 hours, the building are able to construct all the structural and non-structural components are assembled. The lights are turned on, the water is running, the furniture are put in. So within 6 days, less than 7 days, we have a brand new 15-story hotel that we can use. This kind of new technology are being heavily investigated around the world. In fact, in China, they are thinking of building the next tallest building in the world, 220-story, using fast construction technology. Right now, in China, for the modular construction technology, if you don't use it, you may not be able to get a permit to build in a city like Shanghai or Beijing. So in North America, we're developing a fast construction technology. Buckling restraint knee brace truss movement frame is one of the technology that we have collaborated with our colleagues around the world. So the idea of it is using truss that you can use this in regions to create large interior spacing. To ensure it's performing well for earthquake, we started developing energy dissipation devices to dissipate energy. And we have secondary devices to dissipate additional energy. So in the laboratory, we tested many of those devices that we developed, and we're working with Star Seismic, now called Brace, to developing those damper technology. And we developed simulation model to demonstrate that the structure can actually work well and very well during storm and earthquake shaking. So the device can yield and dissipate the energy throughout strong earthquake shaking. After it's done in numerical simulation and experimental testing, we then the structural system will be placed. All the electrical, mechanical, and plumbing system are put in the factory. We put in the floor, the fire coating, sound insulation, and fire coating on top, and then we can easily ship to the site. On site, we can quickly place, using very limited amount of crane and humans, then we can place those columns and lift the floor to place and make sure it works for high seismic zone like Indonesia and in Vancouver. We started putting these energy dissipation devices. The device can be very quickly, the structure system can be very quickly constructed using very limited amount of human. And the system, it's very lightweight, very fast construction, and is earthquake resilient. So we can easily deploy it to many locations around the world. The system can be placed in groups of modules and places together, and we can create a very large opening spaces, no different than this rendering shown on the slides. The other technology that we have developed here in North America is reusing the shipping container technology to build housing, because we have many shipping containers left in the North Shore and then we needed to reuse them. And our goal is to quickly assemble them so we can solving the housing issues in Vancouver. So we put the shipping container in the factory. We put in the electrical, mechanical, the kitchen into the module, and we quickly ship into the site. To make sure it works for sites, we put the modules on top of each other. And we developed the special bonding mechanism between the modules very, very fast without concrete to cure. Those panels very easily inside those individual units. They are furnished kitchens with cabinet, water, everything is running. So this is the type of construction that we can quickly addressing the housing market. Very recently, just like Indonesia, Vancouver, Canada, Canada in general, have abundant resources of wood. Okay, Canada and Indonesia are both countries exporting woods for resources. Very recently, we started developing high-rise buildings using timber construction. So we started engineering the timber, putting into cross-laminated timber, so we can start reaching to new heights. This is one of the tall 18-story timber building that we built here at the UBC campus. This is another project in Canada. So the idea of another technology that we're doing is start developing this timber glulam columns. We can create DOT floor system, which we can easily manufacture, very, very light, to bring it to site, and we can assemble them. After we do all system into the slots which pre-located, once one floor is done, we started going to the second floor and continue. In terms of the interior finish, we started developing volumetric modules that we can quickly insert building and then start with another floor system and continue and finishing our high-rise construction. Very recently, on this particular conference, we presented the design of the system, which uses a CLT, a cross-laminated centering conical friction damper, which we developed here at UBC, which is damage-free earthquake, and you will center after an earthquake is done. So it provided very nice, stable energy hysteresis. At the base, in Vancouver, we started using a lot of this pin base because our architect liked those design. We reused them in our design. Here shows some very high-level views of the final design we do. We then develop computer models to it using OpenSeas, something that we static and nonlinear dynamic analysis. In the nonlinear static analysis, we do a nonlinear static pushover, so the structure will actually deform, and the energy dissipation devices will pick up the forces. If continue loading, then the devices will slide through the friction devices and dissipate energy. If the earthquake returned, then the devices will actually have a self-centering force to bring the building back to straight without repair required. So after we did the nonlinear static pushover, cyclic pushover analysis, we then do nonlinear dynamic analysis, and we do lots of time history analysis using incremental dynamic analysis procedure. We select a whole bunch of ground motions suitable for the particular site, which is in Vancouver. And the time history analysis demonstrated the energy dissipation device was able to dissipate energy and come back plumb without any residual displacement. And from the large array of nonlinear incremental dynamic analysis, we started pushing and increasing the level of shaking until the structure reaches yielding in one of the devices that we do not allow the failure mode. By doing so, we can quantify the performance of the building using probability of collapse. In that situation, it's actually not collapse. This is a failure probability. based on the study that we show, the structure has a collapse margin ratio about 1.79. So what it means is that about 50% of its capacity, 50% of the time, the capacity, the median capacity is actually about 1.8 times its design level. If you account for the spectral shape factor, the adjustable collapse margin ratio is about 2.27. So very, very robust compared to the acceptable collapse margin ratio. This superior system actually performed very well according to the North American code. Very recently, with advancement of AI technology, we started working very heavily into making this kind of new structure system be built using robotic technology. We started developing virtual reality technology, building information technology, robotic construction technology, and digital twin technology to allow us to make those buildings without much human intervention. So we are starting doing the structural design, but now we have integrated with our virtual reality model, so we can actually see everything before it's being built, and we are developing our robotic technology to assemble those systems. Yeah. So now let me give you some quick summary and conclusion. Next are being developed, and we're making the next generation structures lower initial cost, faster to build, higher performance, smarter, and environmental friendly. I'm very sure, together with our colleagues in Indonesia and around the world, I'm sure we can make a significant difference. With that, I would like to thank you for your attention and look forward to have the opportunity to welcome you all to beautiful British Columbia, Vancouver, and hopefully have the opportunity to re-meet my close friends in Indonesia again very soon. Thank you, Professor Afriyadi. I'm done with the presentation.
Thank you. Let's give applause to Professor Yang. Is it possible to have one or two questions, Professor Yang? Oh.
Thank you. Yeah, I'm here. Absolutely.
Okay. The audience, if you have one question that will be delivered to Professor Yang, could you please raise your hand? No, Professor Yang. So in your presentation, you present that you developed the sub-center canonical damper for timber buildings. Is it possible also that damper is applied to other types of buildings like concrete that may be heavier than timber? That possible?
Yes, Professor Afriyadi, you are thinking correctly. Actually, those dampers are developed originally for concrete core wall, and we have already built some testing for it, and now we are only applying for this CLT shear wall. So yes, you can apply it to other type of system.
Okay, thank you. There is one thing, participant that will raise the question
Sure.
from the Zoom meeting. So could you please tell your name and then? Okay, go on.
Okay. Thank you for the opportunity. Actually, I'm really impressed with your presentation from Professor Tony Yang. I want to ask about your opinion. I've heard about the high-rise building in Helsinki, Finlandia, where all the materials is from wood.
Hello. Could you? Your voice is not very clear from here. Could you? I'm not sure whether Professor Yang can hear clearly.
It's not clear to me too.
Yeah, not very clear. Could you?
How about now? Can you hear my voice clearly?
Stephen, if you possible, can you type it in the chat? Maybe I can answer it, and I can repeat your question.
Okay. I want to ask about your opinion about the high-rise building in Helsinki, Finlandia, where all the materials are from wood.
Steve,
Is it possible
I
or
didn't hear that very clearly. I heard about high-rise building and can you repeat again?
I want to ask about your opinion about high-rise building in Helsinki, Finlandia, where all the materials are from wood.
Can you type it?
The high-rise building in Finlandia, and what is the problem?
All the materials are from wood.
Professor Afriyadi, did you hear that? I didn't understand the question.
Not very clear actually. So maybe could you write your question on the chat? Maybe I have to come forward. Sorry.
Don't worry. It's already very amazing. I'm sitting across the ocean and we can talk. Very good. Yeah.
Can you write your question on the chat?
Yes. Wait a minute.
Not yet.
Materials.
Ada, kami. Oh yes, I want to ask about high-rise building in Helsinki, Finlandia, where all the material are from wood.
Okay, so what's the question?
Maybe you can read also from the chat. But the question is, I want to ask about high-rise buildings in Helsinki, Finlandia, where all the material are from wood.
Yeah, but what's your question? Are you saying that it's possible, or what's that question mean? So my opinion, whether it's a
You just give your opinion about the high-rise buildings in Helsinki.
Okay. Steven, I am not familiar with this particular
countries. We have code, design codes. We have also construction guideline that we have to follow. So how to initiate those situation? Suppose in Vancouver, you start to build this kind of innovative building.
Correct.
Do you need any permission or the permission from a kind of peer review or something like that at every region that you want to build your creative building? Thank you very much.
Thank you, Professor. Okay, Professor Yang, you could answer.
Yeah, Professor Suhendra, thank you for the good questions. We are pushing on the boundary of the technology, and every time a new technology being made, it's always creating challenging in the way we implemented them. So in North America, what we have been doing is that we do peer review for this kind of structure system. And the peer review will require experts like yourself or myself who are expert in the material level, in the structural level, and in the ground motion level, and then on the modeling. So that a group of peer reviewer will review projects like this. As a matter of fact, in America, United States, almost all buildings, even is made with the traditional technology, we are all going through peer review these days because it all break the high limit what the code is doing right now. But I believe that's where the future is going, where the building code stop giving you detailed guideline how every building need to be designed. It will give you targeted performance, how the building need to achieve. And you as an engineer, and there are many great engineers around the world, are able to design the building to achieve the performance you want. And hence, we are moving towards this performance-based goal of a new structural system. I hope that answers your question.
Okay, thank you. I think you have
Thank you.
answered the question very well. I think because of time, so we have to finish this session. So I think let's give a big applause to Professor Yang. But before Professor Yang leave, I think certificate of appreciation, digital certificate appreciation.
Thank you. Highly appreciated. Thank you so much. Thank you.
Okay, again, thank you for your interesting presentation. Although in the beginning we have problem, but this is really very interesting. Thank you again, Professor Yang.
Thank you, everybody.
Thank you for your time.
Look forward to seeing you. Bye-bye. Thank you.
Okay, thank you. Bye-bye. Okay, ladies and gentlemen, we will continue to the second keynote speaker. So the Tanaka. So Professor Hitoshi Tanaka,
yes,
is professor in Tohoku University. His expertise is coastal engineering, hydraulic engineering, environmental hydraulics, and he obtained his PhD in 1984 from Tohoku University. He has several publications. The recent one of them is The Necessity of Using a Wave Friction Factor in Tsunami Numerical Simulation. And he has also received award from APD Distinguished Membership Award at IAHR in 2016. Professor Hitoshi Tanaka, have you joined the meeting? Okay. Could you check the presentation maybe before I give you? This.
Thank you very much, Professor Piadi. Can you hear me?
Yeah.
Transport by tsunami waves. And a similar phenomenon